Hey friends, it's the Rocket Noob, and here we talk about building and flying model rockets and high-power rockets. And how you doing tonight? Tonight we are going to be designing from scratch a high-altitude two-stage model rocket. And if that sounds ambitious, well, it might be. But believe me, this is a rocket that a relative beginner can build on their own, and so it's not going to be a big deal. We're going to have a little bit of fun tonight. Last week, if you happen to see the stream, we designed a rocket from scratch using the software called OpenRocket, which we're going to do tonight. Last week, it was a little bit sloppy. We just kind of made it up as we went along, and I just didn't like that so much. So I've decided to come up with some parameters. So let's bring up our parameters here, and they're right here. So we're going to be doing a two-stage model rocket. It's going to carry a payload, which in this case is going to be an altimeter. It's going to be a simple build, meaning it's not going to have any crazy techniques that like relative beginner to model rocketry can't do. And it's going to have off-the-shelf parts. What do I mean by off-the-shelf parts? Well, so we are going to be building a rocket that flies relatively high, but it's going to be a sport model. It's going to be, that's what we call a rocket that's just a fun rocket. So there is competition rocketry, and there are some really elite competition rocketeers. And when they are going for altitude, they might make their own materials. So, for example, they might make their own tubes out of very lightweight fiberglass cloth and epoxy. And what you end up with something is paper thin and extremely light. But it is a little tricky to make. It's got some hazardous materials involved. And, you know, what we're trying to do here is have fun and come up with something that flies really high. We're not necessarily trying to break any records and not necessarily trying to win any contests. Although maybe we can talk about what it would take to build a contest rocket later. So let's see. We've done our parameters here. So we've got the two-stage payload, simple build, off-the-shelf parts. So first what we're going to do is we are going to go to my desktop here, and what we're going to use is a program called OpenRocket, and this is free software. It's free open source software you can get from openrocket.info. You can download it. It runs on anything, Windows, Mac, Linux, whatever you got, it will run. And it's a fantastic tool. It's a fantastic free software that is available. And the things that you can do with model rocketry today and high-power rocketry are really astonishing. A lot of people think of the golden age of model rocketry as like the 60s and 70s, which was great. But there's just so much more you can do today with the materials you have, with electronics, with, computer software. So it's really great. In the old days, if you wanted to design your own model rocket, you could do that, but you had to have some drafting skills in order to do it accurately. There were some math skills that were involved if you wanted to find your center of pressure, which is part of stability, which we'll talk about as we get into this. And those are great things to have. As a matter of fact, I think looking at the old way of doing model rocketry, if you were a teacher, say a math teacher, is a great project because kids can learn how to use mathematics to find the center of pressure on a rocket and tell whether it will be stable or not in flight. But OpenRocket is a free software. There is one called RockSim, which is available from Apogee Components. It's not free. It's pretty expensive. It's a great program, but OpenRocket is great for beginners and advanced rocketeers alike. As a matter of fact, I know some advanced rocketeers, high-power rocketeers who only use OpenRocket, and I know some who use both OpenRocket and RockSim because they kind of like having a second opinion, as they put it. Anyway, you just download it and you open it up, and let's go to my desktop here, and we're going to go ahead and open up RockSim. Now, OpenRocket. Yeah, there it is. I have several versions on my desktop, and I tried to clear them all off, and I think I accidentally left a couple of them on. So we're just going to open it up. So then one of the first things that we will want to consider is what parts do we have? We're going to design this rocket, and we could design it basically any dimensions we want to. but then we might have to make parts. And what we're trying to do here is actually, for beginners, we're trying to use parts that are commercially available, so we don't have to make our own tubes, we don't have to make our own nose cones. If you want to do that kind of thing, there are people who do that, but that requires some advanced building skills. And in any case, we've got parts available to us that you can easily acquire, that you can use and put into practice and build these rockets. So let's start by going to one of the websites where you might find these. So there are several websites that I like to shop at if I'm looking for parts. One of them is called johnrocket.com. This is one of the first suppliers I ever shopped from. John Rocket, that's JONRocket.com. There's no H. And we're going to go down to parts, and we're going to look at nose cones. And so what we are going to look for is we are going to look for something called a BT20 size nose cone. One of the first things that we need to do if we're going to fly really high is we need to make a rocket that is as skinny as possible. So what we really need is we need lightweight and low drag. So we need a lightweight rocket, and we need a rocket that doesn't have a lot of drag or air resistance, basically. So a big fat rocket like, say, the Big Bertha, which is a nice big model, doesn't fly very high because it's bigger, so it's got more material, it's heavier, and it also is big and fat and has big fat fins, and that increases the aerodynamic drag, which is gonna lower your altitude. And if we're gonna fly really high, we want something really skinny. Let me show you what I'm talking about. I'm talking about something that is going to be no bigger in diameter than the engines we're going to be using. And in this case, we're going to be using commercially available Estes motors, and they are 18 millimeters in diameter. And a lot of rockets that you might build, such as the Big Bertha, they have a big tube, and then they have a little tube inside called the engine tube or motor tube. And then you have a couple of rings that are called centering rings. And if you've ever built a model rocket that has centering rings, the purpose of that is to keep the engine tube right in the middle of that big fat tube. Well, that means that you've got all this extra wasted space. If you're trying to fly high, you want something skinny. You want something called minimum diameter. In other words, you want something where the rocket itself is only as big in diameter as it needs to be to accommodate the engine. So the body of the rocket is the engine tube. There is no engine tube or motor tube inside the rocket. It is the engine tube. And there are a few kits that you might be familiar with that are minimum diameter. One is the Estes Viking. It's a skinny little rocket. It has some cardstock fins. It's a pretty simple rocket to build. You find these in bulk packs and classroom packs a lot, and they're pretty simple. They don't require a lot of special finishing skills because the fins are smooth. They're made out of cardstock. And then another one is the Estes High Flyer, which I lost because it flew so high. I couldn't find it when it came back down. And that's another minimum diameter rocket. These rockets fly really high because they're so skinny. They're lightweight, and they just don't have a lot of drag. Because of that, I don't necessarily think that they're the best rockets for first-time Rocketeers, because being so small, they tend to get lost. But for our purposes, they're great. So I have a prototype, a couple prototypes here of a minimum diameter rocket. So this is the diameter we're talking about. It's pretty small, and you can see the engine fits right in there, and there's no additional room. That's called minimum diameter, and for a high-flying rocket, that is what you want. Now, the size that we are talking about here is referred to as BT20. Body tubes, BT stands for body tube. Estes has a whole range of sizes, from BT5, which is very skinny for little miniature engines, up to BT60, which is your Big Bertha, if you're familiar with the Big Bertha, Dured Max, up to BT60 and BT80, and those are 2.6 inches in diameter. Those are nice, big, larger rockets. So what we're looking for is BT20, and what we're going to start with is a nose cone. When you build in OpenRocket, you start with a nose cone. So let's go back to John Rocket here, and we have a number of options here. So we're going to scan, we're going to scroll through here, and we're going to find our BT nose cones. So we have some balsa options here. This is a balsa nose cone. Balsa is nice lightweight material. It does take some work to make it nice and smooth. If you want to make it smooth, reduce drag by making it smooth, make it easy to paint. This one I'm not that familiar with, but it's sort of an ogive nose cone, and it's about 1.7 inches long, and it fits inside a BT20. We've got a little sort of a longer, pointier nose cone here, and we've got some plastic from Estes. It's sort of a 4-pack of various shapes of nose cones for the BT20. Another great site is ASP Rocketry. ASP has a lot of great stuff, especially balsa parts. And so we're going to look at nose cones. We've got several here that are really nice. I like this one. This one, the B-shaped nose cone. It is kind of a sort of an elliptical shaped nose cone. There you can see. This kind of slightly different elliptical nose cone. We got a little cone-shaped one. We've got a pointy ogive here. We've even got this straight-up conical-shaped nose cone. That's quite nice. You can get them from AC Supply. AC Supply sells rocket parts. Let's see. And I think this is where I got my nose cones that we're going to be working with tonight. You can buy just parts and supplies like parachutes and nose cones. Like you can buy multi-packs of nose cones from AC Supply. AC Supply is great because it is a discounted supplier of Estes parts and Estes items. If you saw my video, where to buy model rocket supplies, not just Amazon, I mentioned AC Supply. Now, I did mention that they sell things at I think it was a 30 or 40% discount. The rules have changed slightly because Estes put some pricing rules in place. So when you just go there, you may not necessarily see discounts on the rockets, unless you log in and add it to your shopping cart. Then you will see discounted prices often. But here we have just a 10-pack of these BT20 nose cones. And these are the same nose cones you will see with a lot of kits like the Viking and the High Flyer. Another option is balsa machining service, and they hand make balsa parts. The thing about balsa machining service is they do great work, but when you look at the parts, what you're looking at is this little diagram here, which may not tell you much when it comes to what it is you're getting. But they do great work. A lot of people swear by balsa machining service. And, of course, you could go to Estes as well. Estes does sell nose cones, but the only nose cone we're going to find here, let's see, what we're looking for is accessories. We're looking for building supplies. We're looking for parts, nose cones. So the only BT20 nose cones that I found here on Estes were this 4-pack of... of nose cones. I mean, it looks like we have one. We've got one of the longer pointy ones that you'll find with those kits that I mentioned. You have a sort of an elliptical one. This short little one that doesn't look like much, and then this conical one. I love Estes, but I think this is just a little bit much to pay for this 4-pack of nose cones that I don't think half of them I wouldn't want to use anyway. So I actually happen to have a bag of nose cones, and these are the plastic ones. Balsa might be lighter. I don't really know, but I'm going to go with what I've got. So if you're building a contest rocket, you might need to compare what's the lightest you can go with these. But these are a pack of nose cones I got, and I'm pretty sure I picked these up from AC Supply. They come in 2 pieces. You've got the cone, and you've got the little cap that you have to glue in with either plastic cement or super glue, and then you can attach your little shock cord to that. And they're very lightweight. So one of the things that you'll want to do when you are designing for altitude, you might consider getting a scale so that you can weigh parts. And I have a couple of different scales. This one is basically a jeweler's scale from AWS. It's accurate it uses grams. It's a metric scale, and it's accurate to 1/10 of a gram, which is great if you're building little rockets. For a lot of other purposes, I like to use a kitchen scale. This one is by Ozeri, and it's my kitchen scale. During the pandemic, I was one of those people who started doing sourdough bread. I didn't realize it was a trend. I just knew that I didn't want to go to the supermarket very often, and I wanted bread for my family, and I couldn't find yeast. So I thought, well, maybe I could make sourdough. And so I ordered this. This is America's Test Kitchen's like Best Buy, and it's only like $9 or $10. There is a link in the description, by the way, for both of these items, and they're Amazon links, and they are affiliate links. Doesn't cost you anything, but if you happen to buy something, it supports the channel. So I use that one for cooking all the time, but I also use it for rockets. As a matter of fact, I use it for anything up to my 4-inch high-power rockets because I can balance everything on there. You might also, if you get into really big rockets, want to get like a postal scale. I do have one. It's a little bit fussy unless I plug it in. But for little bitty rockets, what we're going to use is this. So we have this nose cone, and we're just going to weigh this nose cone, see what it weighs. And it's exactly 5 grams. So we know that this is pretty lightweight. We're also going to be flying some payloads. We got some altimeters, and we're going to be using the scale for the altimeters as well. So what we're first going to do is we're going to input. Let me just check the stream health. The stream is still buffering. You still there, Kevin? I hope Kevin's still there. Anyway, we are going to be going back to OpenRocket here. And what we're first going to do is start with a nose cone. So the first thing that it's going to do is going to pop up this dialog. Now you can choose not to have this pop up if you want, but it will. It's like a library of pre-selected parts. And this is what we're doing here is we're using an Estes BT20 nose cone, and it's a plastic BT20 nose cone. BNC stands for balsa nose cone. Probably. I mean, it does. And PNC stands for plastic nose cone. Pretty convenient. So we've got one, and it is, let's see here. If I'm looking for the right one, how long is this one? This one is 1 inch. This one's 2.65 inches. The one that I actually have, I think that this is OpenRocket's version of this plastic nose cone that I happen to have. But I think this one, having measured it and having judged from the website, is actually slightly longer. I think this one is actually 2.75 inches long, and you're just talking about from the shoulder to the tip of the nose cone. The actual shoulder itself does not count as far as the length. Now, even if I were to leave it at 2.65 inches for the purposes of the design, it's not going to make that big of a difference if it's slightly inaccurate. You can make little mistakes with OpenRocket, and it's not going to be the end of the world, but I do try to be as accurate as possible. So we're going to set that at 2.75 inches. It is a polystyrene nose cone. Now, when you just put in parts without having pre-selected something from the parts library, everything is going to default to cardboard, and you have to change it because different materials weigh different amounts. So we're going to go ahead and select that as our nose cone. Now, what we want to be able to do is carry a payload. So that means we need a payload section, and we need a tube, and we're going to use just regular paper, craft paper, or cardboard body tubes, which you can get from all of the suppliers that I've mentioned. These are BT22 tubes. You can see they're just the right diameter to install a nose cone, or to install an engine. I need to check the chat because I don't trust that I'm actually streaming right now. Stream status is poor. Well, I'm just going to keep going, and if I have to do this again, I have to do it again. All right. Well, let's go back to OpenRocket. Anyway, so yeah, you got your BT20, so you want to cut these to length, or you want to buy a payload section, and then you want something to block the ejection charge. So you want your payload to be just in one little section of the rocket, because the engine is going to be down at the bottom, and it's going to power the rocket, but then at the very end of flight, there's going to be an explosive charge, an ejection charge, that's going to pop off your nose cone or pop off your payload section in any case. And you don't want the corrosive gases from that ejection charge to get into your payload, especially if you're flying an altimeter. That could gum up the works and kind of ruin your altimeter. So we need what's called a bulkhead. And in this case, these are from AC Supply, these tiny little plugs made out of balsa wood. And they're made to fit perfectly in here. So it's about 1 inch long. It's halfway in, halfway out. I thought I had some of these that I hadn't glued in. I couldn't find them. They're very lightweight. They're very small. You glue it halfway in, and so now you have a sealed chamber for your payload, which goes right in there when you fly. And this one is 2.75 inches in length, I think. Let me measure it. Yes, 2 3/4 inch. The reason I did that is I got a bunch of these for a project. They have these payload kits, and I wanted the payloads that I made to be exactly the same as the payload kits, which also come with their own bulkheads, and they come with these little screw eyes. So anyway, we're going to add a body tube here, and we're going to make it 2.75 inches in length. So now that I've got my nose cone selected, I'm going to click on body tube. And we're going to select an Estes body tube, a BT20. And let's see, we've got an 18-inch one. We've got a 6.5. We got a 4. It doesn't really matter. You can see that the outer diameter and inner diameter are the same. All that changes is the length of the tube. It doesn't really matter. I'm going to go ahead and change the length of the tube anyway to 3.75 inches. I'm just going to select one of those body tubes. Now, because this is made out of spiral wound craft paper tubes, it's going to assume the weight based on the average of how much these tubes weigh per inch. And so we're just going to use the weight that it assumes as we're building the rocket, just to get a rough idea of the weight of the rocket when it's finally built, and then we can get an idea of how high the rocket will fly. But it's important to note that the materials you use may be slightly different from the materials that you are simulating, and so when you build the rocket, when you finish the rocket, you need to weigh the rocket. That's why it's good to have a digital scale, so that way you can input the information and see how high your rocket would fly. Of course, the best way to see how high your rocket will fly is to include an altimeter, because every simulation has to be taken with a grain of salt. So, hey, I think we are back in business with our stream health. So, all right, so we got our nose cone, we got our payload section, and now we're going to add our balsa bulkhead. The balsa, this is when you buy these little balsa bits on here, they are called, I think, engine blocks or nose blocks. They're not called engine blocks. Engine blocks are these. We'll get to these. They're called nose blocks by a lot of websites. But in this case, what it is a bulkhead. It's sealing off two completely different compartments. So we're going to add a bulkhead. And we don't need to necessarily select the brand. I don't really care about that. We are just going to make sure the diameter is correct. And the thickness, this is a 1-inch thick bulkhead made out of balsa. You can see that I just selected a generic component, so it selected cardboard. I'm going to select balsa wood, because that's what this is. And this is the bottom of our tube. It's also the, you know what? I'm not on the right. You're not seeing what I'm doing here. Oh, so sorry. Okay. Let me go back a few steps. All right, so we undid that. We're going to undo our preset body tube. So we got our nose cone. We're going to redo adding our body tube. I got a little monitor so I wouldn't do that this time, and I did it anyway. Then we're going to shorten the body tube. Then we're going to add the bulkhead. So you can see that this here is, let me get my face out of the way. No, not that. This here is the bottom of our body tube for the payload section. It's also the bottom of our bulkhead. We need the bulkhead to be halfway in and halfway out of the tube. So this is 1 inch bulkhead. So I'm going to select the bulkhead and I'm going to add it plus 0.5 inches. Now I'm using inches here for a lot of the parts. I live in the United States. I grew up with inches. For certain things, I will use metric, especially when we're talking about the diameter of motors, because that's what they do. Diameters are always done in millimeters, and with American model rocket companies anyway, lengths are often done in imperial units, and so is the thickness of the balsa sheet, you know, except for Quest Aerospace. They use metric. But in any case, we're going to be using, I'm going to be switching back and forth. There are some things I actually just prefer to use metric for, just because the units are smaller, they're divisible by 10. Let me move my face up out of the way here. So anyway, so we got our bulkhead, we got our nose cone, we got our payload tube, and we've got our bulkhead. Now, one thing I will try and show you here is that this already pre-made payload tube, I don't know if you can see this, it's going to be a little difficult, but it's got a teeny tiny hole in it. It's actually got 4 teeny tiny holes in them. So I'm going to fly an altimeter in this rocket. And an altimeter, what it does is it measures the altitude of the rocket by taking air pressure readings. And in order for it to accurately judge the air pressure as it ascends, it needs to be ventilated. The payload section needs to be ventilated. So this is going to be tightly closed off with the nose cone. So you've got these little tiny holes, and these are called static ports. For larger rockets, you need to use a drill, and there are calculators online that you can tell that will tell you how many holes and what size they need to be. For these tiny little rockets, though, I just basically mark where I want them, and I take a push pin, and I make a little tiny hole in there. And so that it makes a nice, neat little hole, and I've got 4 of them all the way around. So that will enable the pressure to equalize as the rocket ascends, so that I will get an accurate reading for my altimeter as I'm flying it. So now I've got that body tube there. I've got that bulkhead there. We do have also some hardware here, and I don't actually know how much these weigh. We'll just ignore the screw eye for now. When we're done building the rocket, we're going to weigh the whole thing anyway, and we're going to find the center of gravity. So even if I don't put the screw eye here, I think we're going to be okay. So what I'll do now is I'm going to copy this body tube, and I'm going to paste it, and I'm going to get rid of that bulkhead. Because I need now the lower, I'm just going to lengthen it. We need the lower part of the rocket. And I think I'm going to make this 6.75 inches long. All right. Let me check the chat here, see how we're doing. We're doing okay. And once again, I forgot to show you my screen. All right. Go back a couple steps here. All right, so here's my payload section. Then I just copied and pasted this tube down here, just so that it would be the same kind of tube, because I cut these parts. I've already made sort of a prototype of not exactly the rocket I'm going to build tonight, but something similar. But I cut these parts from the same tube, so I'm just going to get rid of that extra bulkhead. And I'm going to take this tube here, and I'm going to lengthen it to, I think, I can't remember exactly how long I wanted this thing. I'm going to say 6.75 inches. There we go. Now, this is our lower body tube, but it's also our motor tube for our upper stage. So we need to click from General to Motor and select this component is a motor mount. And that will enable us to put a motor or engine inside. And we're going to have this engine overhang by about 1/2 inch. So this is, let me show you the, I'm going to hit click OK. Let me show you the prototype that I have of, this is a 2-stage rocket that I built. It's a similar idea. And we're going to have the motor overhang by about 1/2 inch. So you can see this engine here is sticking out a good amount from the back of this rocket from the upper stage. Now this could fly as a single stage rocket. It would fly great. It would fly very high. It'd probably go well over 1,000 feet, 1,200 feet. We can do better. And I'm going to tell you why I want this motor sticking out so far in a little bit. But for now, we are going to make that our what we're going to do. We're going to have that stick out about a 1/2 inch. Now, in order to keep the rocket engine from going all the way into the tube, we have to use an engine block. And this is, I weighed this earlier, this is about 3/10 gram. It's just a little cardboard ring. It gets glued inside the rocket at a certain depth, and that will keep your rocket engine from going too far in. So, for example, here's another prototype. It'll go that far, won't go any further in because I've glued one of those rings in there. So we're going to add that. It's going to be an engine block. And we are going to, I think the one we're going to select here is the balsa machining one because I think it's the closest in size to our actual bulkhead or our actual engine block here. It's 3/10 gram, and I'm going to move it up inside, and we're going to move it up 2.25 inches inside. So these little standard engines, and I'm once again not showing you my screen. Okay. So these little engines are 2.75 inches in length, or about, is it 70 millimeters? It's 70 millimeters in length if you were doing metric. So we're going to move the engine block here, this bit here, that far in, so that when we get a motor and stick it inside like this, S to C, let me find the S to C. Come on. S to C6 motor. Now you can see that the motor sticks out, but it's being stopped by the block, right? So that looks right. So we're gonna go back to our new. We're just gonna delete that motor for now. I think my computer's being slow. Cancel. All right, so we got nose cone, payload section, bulkhead, body tube, engine block. Now comes the fun part. We're going to put the fins on. So, if you are building like a competition rocket, you're going to go for the thinnest fins you can possibly go for. You might use thin sheets of carbon fiber or fiberglass. so that you have as little drag as possible. We're going to be just using standard model rocket building materials, so we're going to go for balsa fins. And the thinnest that we're going to go for right now is 1/16 of an inch. Can you get higher altitude with something thinner? Sure, but we're going to get plenty high with this rocket with some balsa fins here. So we're going to go with trapezoidal fins. When you first put them on, they're going to look a little funny. Yes, we're going to select the body tube, and we're going to go for trapezoidal fins. They're going to look a little funny. They're going to be basically parallelograms. So the question is, do you want 3 fins or do you want 4 fins? You can have more, but the more fins, the more drag. Now, generally speaking, the more fins you have, the more drag you have. But one of the things that fins do is they move your center of pressure aftward. You need your center of pressure, which is this little red dot here. You need that behind your center of gravity, which is the little blue and white dot here. And in order for that to be stable, for the rocket to be stable and fly straight up and not flip around. So your center of pressure is like your aerodynamic center of the rocket. It's like your balance point, your aerodynamic balance point. And it has to do with the surface area of all of the parts and how they interact with the wind as the rocket is flying through the air upwards at hundreds of miles per hour. So the more fins you have, the further back your center of pressure will be, and the more stable your rocket will be. But also, of course, it adds weight to your rocket on the backside. So you see the center of gravity is moving backwards. But there is such a thing as too many fins. So we're going to... so you could go with 3 or 4. Now, a lot of people, when they're shooting for altitude, they go for 3. The difference between 3 and 4, if you get the same margin of stability, in other words, the same distance between the center of pressure and the center of gravity, is going to be minimal, because with a 3-fin rocket, you're going to have slightly larger fins than you will have with a 4-fin rocket. You'll still be able to get slightly more, probably 20, 34 more feet out of the rocket. And generally speaking, if you're going for ultimate altitude, 3 is the way to go. That's what contest rocketeers do. But you don't necessarily have to. You can still get plenty of height, plenty of altitude out of a 4-fin rocket. Now, I actually like 4 fins. I don't like these fins. I don't like the way they look. So we're going to change the dimensions. So the chord is the distance from the leading edge to the trailing edge. So the root chord here, we'll just make that. We'll start with making it 2 inches. Why are we having trouble? Come on, 2 inches. There we go. And then the tip chord, we're going to make a little smaller. We're going to make 1.75 inches. And the height, we're going to make 1.75 inches. That's pretty big. We're going to make that smaller. So here's the part where you can play around with all kinds of things. You can make your own shapes. You can make, so we made, we're making trapezoidal fins. You can make freeform fins that look, whatever way you can draw your own fins. You can make elliptical fins that kind of are sort of semicircular. If you look up here, you got trapezoidal, elliptical, freeform tube fins. You can just stick a series of body tubes around the body of the rocket, and those will act as fins and stabilize the rocket. But I like trapezoidal fins because I'm very traditional. So we're going to make these sort of smaller. We're going to make that 1.75 as a root chord. We're going to make the tip chord 1.5, and then we're going to make the whole thing shorter at 1.5, and just see what that looks like. And that still looks a lot bigger than I like. Here's what we're going to do. We already have a motor tube selected. And in order to get our biggest altitude, our highest altitude, we need to make sure that we have a stability margin of 1 body tube diameter at a minimum. What that means is the center of gravity and the center of pressure need to be at a minimum as far apart as the diameter of the body tube, if that makes any sense. So if I go ahead and put all the parts in, and then I can play around with my fins, I can get the fins as small as I need them to be, or as small as I can get them without needing to be any heavier, because I will have an idea of what my stability margin will be. So let's go ahead and add in our recovery system. So first things first, let's add in our payload. So we have a number of altimeters here. I've got a number of altimeters here. This one is by Perfect Flight. It's called the Firefly. It's very tiny. It's great. It tells you the altitude by flashing at you. It'll flash, it'll flash a number of times, and that'll tell you 1,375 feet. So it'll flash once, then 3 times, then 7 times, then 5 times, and that's 1,375 feet. It measures altitude in feet. This one I love this one, but I really wish it was still available. This one is by a company called Flight Sketch. And this is a project that somebody started, and I don't know if it just became too much for them to continue making these. These are great altimeters, and the problem is that not only can you not find them anymore, but it requires an app to use them, and the app is no longer available. Now, I have an app. I have the app on an old phone, but you can't download it anymore. So I have a few of these, and the Firefly is 3.5 grams in weight, and the Flight Sketch is 3.1 grams, and it's great. It's great because the app would show you, like, flight data mapped out on a curve. But we're gonna probably go with the Firefly in this case. One other one that I have, which I really like, is the Jolly Logic. This is the Altimeter 2. The Altimeter 3 uses Bluetooth, so you can actually get information on your phone. I didn't have a phone that was really capable of, taking advantage of it when I got this one. This one is 10 grams, so it's a great altimeter, but for what we're going to do, it's quite heavy. It's much heavier than the Perfect Flight. So we're going to add a Perfect Flight altimeter to this payload section. We're just going to select we're going to select our payload section here. Let me get back into the rocket. We're going to select our payload section. We're going to find a mass component, and we're going to rename it Altimeter. And we can even select altimeter on here. So that little symbol with the arrow means it's an altimeter. The mass is 3.3 grams. And length is about an inch. Inch. About 1 1/8 inch. And the diameter is about... It's a little less than half an inch, I think. It's maybe a little bigger than that. Doesn't really matter. So I'm going to make sure that it's stuffed down inside the tube here. So that's going to add a little bit of mass. You can see already we are getting a guess on how high this rocket will fly. As is built right here, it's guessing that we will hit 846 feet on this motor with this design. Now, we haven't finished it, obviously. We need other parts. So we're going to add a shock cord. We're going to use some elastic cord, like a rubber band. We're going to use like an Estes rubber band. Let's just say we have an Estes rubber band lying around. It's not necessarily the shock cord I would use for a lot of things. I would probably use some Kevlar kite string for this because it's lightweight and it's strong. But let's just say we're going to go with, for the sake of it, an Estes rubber band. Why not? Oops, didn't mean to do that. Let's go back to... Some of my numbers are also hotkeys. So we're going to change our length to 18 inches. It's a rubber band. And we want our packed diameter to be small. We're going to plus about an inch. We're going to say it fits right in there. And then we're going to add a recovery device. Now, If you've built model rockets before, you know that a recovery device, it's the part that brings your rocket safely back down to Earth so that it doesn't get broken, it doesn't damage anything, and you can safely fly the rocket again. A lot of rockets use parachutes as a recovery device. In our case, we're going to fly really high, and it's a very lightweight rocket, and we could use a parachute, but if we use a parachute and this rocket flies to as high as we're hoping, then when it opens, it's going to get caught in the wind, and it's going to drift away, and we will probably lose it in a tree or lose it over the flight line, over the horizon. We'll never see it again. So we're going to use a streamer. A streamer is a long, thin piece of basically tape. You can use party streamer. What we're going to use is Mylar streamer because it's shiny. It's metal. It's the same stuff you know birthday balloons are made out of. And it's a metallic, shiny substance, and that way it'll be nice, and we'll be able to see it. It'll reflect the sunlight. So we're going to make it, we'll just make it 20 inches long. We're going to make it 2 inches wide. 1 by 10 is usually the ideal width to length of a streamer. And then, yeah, it's going to be made not of ripstop nylon, but it's going to be made of Mylar. And we're going to packed diameter, we'll say it's, 0.4 inches. We're just guesstimating here. And we're going to stuff it down about 1 inch into that rocket. And again, I am not showing you my screen. Okay. So we're going to... Let me just go back. Redo. Add streamer. All right, so we got our streamer. Let's delete that. I wanna show you the process of adding a streamer. You're gonna go down to Mass Components, Streamer. This is your recovery device. I'm just gonna make my own with Mylar. It's gonna be 20 inches. It's gonna be 2 inches wide. It's gonna be 20 inches long, and it's going to be, we're just gonna say it's 0.4 inches diameter when it's packed, and it's going to be stuffed down in there with the shock cord. There we go. So one other thing we're going to use, of course, if we want to put this on a launch pad, is we're going to use a launch slug. I'm starting to get tired and thirsty. We're going to use a launch slug. Now, if you're a contest flyer, you are probably not going to use a launch slug because a launch slug increases drag. There are other ways of launching a rocket without a launch rod. You can build a tower. You can use a piston. But these are sort of advanced techniques, and I want this to be a simple one that anyone can build. And so we're going to be using a launch slug. So we're going to use just a piece of Estes launch slug for an 1/8 inch rod. And we're going to stick it there, and it's only going to, I think I have some 1 inch long launch slugs, so we're going to make it 1 inch long, and it's going to default to being in the middle of the rocket, and that's probably fine. I want it at about a 45-degree angle if we're going to go with 4 fins. So let me show you what I've got so far, right? Now, this is a complete rocket, basically. It is missing, the only thing it's missing is the little screw eye to attach the top part to the bottom part, but we will add that later. So what we have now is a rocket that essentially looks like this. This is our rocket, and I haven't messed with the fins yet. There are probably too many of them, and they are too big. You can see our stability margin. Our stability margin needs to be at least 1. That means that we need 1 body tube diameter, and the body tube diameter here is 0.736 inches. It's a little over 18 millimeters. So there needs to be that amount of distance between this center of pressure here and the center of gravity, and we've got more than twice that. So we've got lots of room to shave down these fins, and we're just working on the top portion of the rocket so far. This is just the upper stage. We haven't even gotten to the bottom stage yet. So we're going to go back to viewing the rocket. Now, I'm going to make these fins smaller. I don't like the way they look. They look a little goofy. Let's start with the tip cord. So we're going to make it a 1.25 inch cord. Let's make it even smaller. What about 1 inch? What about a 3/4 inch cord? A 1 1/4 inch root, and then a height of, what about that? Look at that. That's not bad. It's a little swept a little far back. Do we like that? Or do we not like that? Let's take a look. Let's take a look at what that looks like. That's kind of cool. They look really thick in this rendering here. But they are only, oh, it's because they're 1/8 of an inch. We want 1/16 inch. Let's see what that does to our altitude. Wow. Okay. So let's look what has happened here. So we're gonna undo what we just did, because look at what where our altitude is for this as a single stage rocket so far. We are currently up to 1,454 feet by making the fins smaller and by making the fins thinner. So if we make the fins back, if we replace those 16th inch fins with twice as thick 1/8 inch fins, we lose a couple hundred feet, 1,288 feet. And then if we go back to the big old fins we had, we are back down to, come on, it's not adjusting. Let's try a flight. Let's do a simulation and run the simulation and see what it's telling us. 843 feet. So for some reason it's not adjusting. There we go. All right, so now we're cooking with gas, because we got nice thin fins. We've got smaller fins. One thing that we don't have though is airfoiled fins. So airfoils, now when you get a kit, as you probably know, the fins are cut out of a sheet of balsa and the edges are square, and you can definitely leave them square. You don't have to do anything special, but a lot of us, myself included, like to change the shape of the fins, and you can sand them into airfoils. These are airfoils. Airfoils are the shape of an airplane wing. These ones on the right here that you're looking at, those are asymmetrical airfoils. Those are what you would find on an airplane wing. You don't want that with rockets because you want everything to go straight. So these are symmetrical airfoils. So basically you can have a piece of balsa that is squared off, and through very careful sanding, you can shape them so that they are not quite like this. That's quite tricky, but you can shape them so that they're much more streamlined like this. And that hypothetically should give you more altitude. So let's try that. So we're going to click on these fins, and you can see that they are currently square. The fin cross section is square. What happens if we sand them into airfoils? What are we going to get then? 1,702 feet for a single stage rocket. Now let's see. I'm gonna switch back to the design view here. I don't really like these swept back so far. They're a little too far back for me. So I'm gonna change the sweep angle. We're losing now, according to this, we're losing a little bit of altitude as I do this. I'm a little skeptical that that's really going to make a huge difference. We are getting closer to a single caliber stability, though, if you look. So we've got we've got airfoils, 16-inch fins, and I'm actually going to move these fins forward slightly. By 1/4 of an inch. And I'll tell you why I'm doing that. Now I've lost my stability margin. I'll tell you why I'm doing that. It's because when you put the motor in, let me grab a rocket here and I'll show you. When you put the motor in, there are a couple of different ways to keep it in. So if I slide this motor into this rocket like that, it's going to fall back out. Now, with bigger model rockets, there's a hook that will hold it in place, right? So this is, for example, an Estes Alpha, and it's a pretty skinny rocket. It flies pretty high, but we can do better by making it minimum diameter. But it's got this hook on the back. So if I stick the motor in here, it's not going to fall back out because it's got this hook holding it in place. Well, we don't have that on this minimum diameter rocket. So we got a couple things we can do with it. We can either wrap tape around it and friction fit it in, which we might do. But the problem with friction fit is it's kind of a tightrope walk. You want it to be tight enough so that when your ejection charge goes off and your rocket pops open, that this doesn't also pop out. You don't want this to come out. So you want it to stay in there. But you don't want it so tight that when you get it back, you can't pull the motor out, which sometimes happens. I don't love friction fit. One other option is to move these fins forward a little bit, and then what you can do is when you put the rocket in, you put the motor in, you can tape some masking tape and just tape all the way around, taping both the motor and the body tube, and you're good to go, and it won't fall out. And that would be an option if we move these fins a little bit forward like we've done here. Of course, we lose some stability and we have to make larger fins, so maybe we make them 0.9 inches. No, we don't even need to go 0.9. We could, what about 0.8? There we go. So now we have a rocket that'll go about 1,678 feet. We can tape the motor in if we want to. We still got 1 caliber stability. What do we get if we make this a 3-fin rocket? 1724. So we gain a little bit of altitude, but now what has happened is we have gotten a dangerously thin. I am on the wrong page. Okay. All right, let's go back. So we've made our fins slightly larger to accommodate the tape. Got a 1.4 caliber stability margin. And then what we've done is we are going to check on with a 3-fin rocket. We get 1,678 feet, but that is a little dangerous because we have a razor thin margin of stability here of 0.424. So that means we have to make larger fins. So we have to make them, let's make them 1 inch tall. 1 inch is too much. What about 0.9? And with larger, no, not quite, 0.95. There we go. So we're back to 1694. So we really don't gain that much altitude with the 3-fin rocket. We gain a little bit, not much. Let's see what that looks like. And, you know, a lot of people love 3-fin rockets. I've got certain 3-fin rockets that I really love. I generally like the 4-fin ones, though. So I'm going to undo all of this, and I'm going to go back to my 4-fin rocket. And I'm going to redo, that's 4. That's 4, right? Yep, that's 4. Yeah, so there we go. So we got a 1.04 caliber 4-fin rocket with a little bit of a margin there where I can tape the motor in if I want to. And yeah, 1,724 feet. That's pretty good. That's pretty good for a single stage model rocket. Let's do a flight simulation. So to do a flight simulation, we're going to go from design. We have picked out a motor configuration. We're going to select the C67, and that's an Estes rocket engine. We're going to run the simulation. So now what this is telling us is that it's going to be 51 miles per hour off the launch rod, which is great. That's plenty fast for stability. It's going to reach an apogee of 1,679 feet. It's a 6.7 seconds is an optimum delay, and we have a C67. C67 means it's got a 7-second delay between when the motor burns out and when the ejection charge goes off and our streamer comes out. It's going to go 365 miles an hour at its max velocity. The flight time is going to be 45 seconds from launch to landing, and it's going to hit the ground at 31 miles per hour. That's kind of fast. So maybe I would want to use a parachute. Maybe I want to use a bigger streamer. It's a very lightweight rocket, though, so that might be just fine. But that does feel kind of fast to me. So we might play around with the recovery device. But for now, that's a pretty good flight. And let's just see what it looks like if I plot it on a little graph here. The red line here is vertical acceleration. So it accelerates for about the first 350 feet. And then the motor burns out, and then it just sort of drops off. It's going to be going very quickly from motor ignition, and it's going to slow down as it reaches its vertical velocity. Its altitude, it's going to continue to coast well past burnout. So it burns out, motor burns out when the rocket's 350 feet. But it's going to continue coasting. Most of the flight is coasting upwards until it reaches apogee, and then the recovery deploys, and then it just slowly falls down to the ground. Very nice. All right. But we weren't here to design a single-stage rocket. We were here to design a two-stage rocket. So I'm just going to check the chat here, see if there's any chatter going on. Greetings from Minnesota. Hey, Minnesota. How's it going? Aero Propulsion's 2.6 inch diameter HI class motor, having never launched a rocket. How stupid is this? I'm not going to call it stupid. I will say, however, that here, since my channel is mainly geared at beginners, and I'm a member of the National Association of Rocketry Standards and Testing Committee, we're buying motors. So I don't make motors. People do make motors, and I would encourage you, if you you may well know what you're doing there, Aero Propulsions, but I would say anyone interested in making their own motors, it's not for beginners, it's not for kids, definitely. It's something where you need a mentor and you need somebody who knows what they're doing, because it is risky. My friend Joe Barnard at BPS Space has a lot of great videos here on YouTube. You should check out his channel. He's going for a space shot, and he's making his own propellants. He's making his own motors, but there are some real risks there because these are some massive, massive motors he's building. I think the most recent one he tested was a P motor, and that video is quite impressive. So when I get a chance, I will link to it in the description. You should check out BPS Space because he's doing some very impressive stuff. Nevertheless, hey, more power to you, as long as you're being safe and you know what you're doing. But you should probably fly a rocket. That would be my suggestion. All right, so we are going to go back to OpenRocket here. All right, now we're back on OpenRocket. You can see my face. You can see OpenRocket. All right, so we want to build a second stage. So there are a couple of different ways we can stage rockets. So what we're going to be using here is two different motors. And in order to fly this rocket as high as we want and as high as we can and staging it, we're going to be using Estes black powder motors, and there are two kinds. We have a C60. The C, the letter, refers to the total impulse. In this case, it is up to 10 Newton seconds. A Newton is the amount of force it takes to accelerate 1 kilogram, 1 kilometer per... Is it 1 kilometer per hour? I actually did bring this up so that I would not sound stupid when I was talking about it. It's the unit of force defined as gives a mass of 1 kilogram and acceleration of 1 meter per second squared, not 1 kilometer per hour. Anyway, so newtons are the force by which the unit by which thrust is measured. Newton seconds are sort of when you multiply the average thrust by the amount of time that the motor burns. That gives you the total power that a motor can give to the rocket. So these C6 motors have about 8.8 Newton seconds of total impulse. Another way of thinking about newtons, I can tell you that 4.45 newtons is about a pound of thrust. Now, newtons are not used to measure weight, they're used to measure force. But if you know what like a 1 pound bag of potato chips feels like in your hand, that's close to about, 5 newtons of force. That force of that potato chip bag in your hand is about 5 newtons. And if you hold that for 2 seconds, that's 10 Newton seconds. That's a C motor, basically. That's the real quick and dirty way of explaining it. So the C refers to the total impulse. The 6 refers to the average thrust in newtons, although the dirty little secret is that some of these Estes motors, that first number doesn't actually match their actual average thrust, but we're going to ignore that for now. And the 0, the second number, is the delay time. So when a rocket is traveling upwards, let's say you've got your little rocket and it's flying upwards, the motor's going to be burning, as we saw in the simulation, then it's going to burn out. But the rocket doesn't stop. It's going to keep traveling. And you want a delay between when the motor burns out and when the ejection charge goes off and pops your nose cone off and pops your parachute out, because you don't want that to happen right at burnout. Because right at burnout, this thing is moving, well, the rocket we're designing is moving about 365 miles an hour. If you popped out your parachute or your streamer at that point, it's going to rip the rocket apart. You want the rocket to continue to climb, and it's going to slow down as it goes higher and higher. And then at some point, you want an ejection charge to go off. With these motors, what you're doing is you're estimating how long is it going to take between when the motor burns out and when the ejection charge should go off. And for these minimum diameter rockets with a second stage, we're going to go for a 7-second delay. And I can't remember why we got into this, because we did a flight simulation. Is that it? Yes. Did I ramble for that long? No, it was because I was talking about motor selection and staging. Okay, so the C60, this is very important. The C60 doesn't have a delay grain, and it doesn't have an ejection charge. You'll notice the regular standard motors have a little cap on top of them, and that's because, let's go to the internet. Let me show you how a 2-stage rocket works. Okay, so this is the components of a model rocket engine. This is from Estes. And so you can see here we have our clay nozzle, we have our propellant, and that's what provides all of the thrust. Once the propellant burns out, we have this delay grain, and that burns slowly. Doesn't really produce any thrust. It's just to allow the rocket to slow down. Once the delay burns up, it reaches this loose black powder, which is a tiny little explosive, and it blows the cap off, and that's what pops your nose cone off and pops your parachute out. So that the second number on your motor, that's what this delay grain is. Now with a 2-stage rocket, you have a special engine called a booster engine, and it's one of these. It's got a 0 as the second number. That means that there's no delay. And if you look at this this page from Apogee Rockets, I've linked to this article down below because it's really fascinating. It's all about how 2-stage rockets work, 2-stage model rockets. I'm going to zoom in here so you can see this a little bit better. Okay, so here we have your standard, on top here we have your standard model rocket motor with a nozzle, propellant, delay charge, ejection charge. Down here we have a 0 motor, right? Like a C60. It's just propellant. There's nothing on top of it. So what happens is it burns, and when it gets to the top, it burns through. And then it will ignite your standard engine, which in our case is going to be a C67 at the top. So there are a couple of different ways we can do this. Now for a lot of model rockets that are minimum diameter, one thing you can do is you can just tape the motors together. So you use Scotch tape, you take the booster motor on the bottom, you put the nozzle on top of the booster motor, you make sure you have them lined up correctly, and then you just tape them together with a single wrap of Scotch tape. What happens is the booster motor burns through, and it ignites the upper stage, and that is hot enough that it will melt or blow off the tape, and then the stages will separate. The booster stage will tumble safely to Earth, and the rocket will continue on, right? In this case, another option is to do what's called gap staging, and that is where you have a little bit of distance between. I wonder if there's any gap staging here. Yes, so you have gap staging. So you have, say you have a booster motor down here, and you have, say, a longer booster. The fins would be here, roughly, right? And then the flame and hot gas that will go upwards will travel quite a bit. You can gap stage for up to 10 to 12 inches. But of course, you need to have vent, because what will happen is the booster motor will blow through, and that's going to create a lot of pressure inside the rocket. As a matter of fact, sometimes I'll see newbies at a model rocket launch try and launch a single-stage rocket, and they will have like a C-60 engine. And if you're at a club, usually they won't let you fly that. The check-in person will say, hey, that's a booster stage motor. It's only for multi-stage rockets. It's going to blow your parachute out at high speed. You don't want that. Sometimes the person working the check-in table is not as experienced as they should be, and it gets through. But especially if you're flying rockets on your own, you don't want to use these -0 motors for a standard rocket. It's only for a booster stage, because it will pressurize the rocket. Well, if you're going to do a gap stage, as we have here, you need little holes to vent the excess gases so that the bottom engine can ignite the top engine and not blow the whole thing off, and then the whole rocket just comes crashing down because the upper stage rocket engine isn't lit. Now, you don't tape the motors together in that case, because they're not close together. You might think that with a minimum diameter, the best thing to do would be to tape them together, and you could certainly do that. But I actually, having built this this prototype before, have done this as a gap stage rocket, and I quite like gap staging. I don't love the taping them together, and the reason is that basically when you tape them together, if it doesn't come off cleanly, it can kick the upper stage off slightly, and then you have a perfectly vertical launch for your first stage, and then your second stage gets kicked off to the side and can go very far, and you could just lose it. And you first of all, you don't get as much altitude as you're looking for because it's not going straight up, and it could potentially go, over the tree line. You lose it, you never see it again. So I actually built this one as a gap stage rocket. This is a prototype. I've tested one before. It worked great. Worked so well I could never find the rocket again. And so what I'm going to do is I'm going to show you the difference here. We're going to put a booster stage on this rocket, and we're going to try the difference between gap staging and non-gap staging. The one thing that you need to do, of course, is you need to vent the booster if you're going to gap stage. And in this case, you can see I've used a push pin, just like I did with the payload section, and I made some little vents, and it worked great. And of course, the way to couple these, if you're not taping them together, is first of all, I've got this motor in here. It's already wrapped with tape to hold the motor in. Well, I've got tape around the back of the motor, and that provides enough friction that the booster stays on, and it works great. It's really nice. I like it a lot. Anyway, get some water. Let's go back to OpenRocket. Let me just check the chat here real quick. We still got excellent health on the stream. It's pretty quiet, but that's okay. All right, so now we've got a single stage completed. Now we're going to go up here and we're going to add a second stage. So the top portion is called the sustainer. The bottom portion is called the booster. So we're going to start with a body tube. Going to use the same Estes body tube we used before. Which one did we use? .5 inches. Okay. This is also a motor mount. And in this case, I don't need the motor sticking out quite so far, so I'm going to have it overhang by about 1/4 inch. Right? Now I'm going to put another engine block in. I'm just going to copy this one. And I'm going to paste it into here. But I don't need it to be hanging out quite so far forward, so it's going to be 2.5. It's going to be, there we go. Now let's make sure I got this spaced correctly. So let me find the motor for this. Come on. It's being a bit slow. S to C60. Okay. There we go. I got my spacing just right. Now you see I have negative stability. That's because this booster doesn't have fins on it. Let's take a look at what it looks like. Yeah, no fins on that. No fins on there. You see it's not giving me an apogee because this is an unstable rocket. So it's not going anywhere. So the first thing I'm going to do here is I'm just going to see if I can just copy these fins here. And then, you know, a lot of times with a two-stage model rocket, you will see the bottom fins, the booster fins, be larger. It's not always necessary. Because you can see here, I now have exactly the same fins on the top as I have on the bottom. And I have a stability margin of 1.24 on the whole thing. So when you're doing a two-stage rocket, you need to make sure that both stages are stable. You need to have the upper stage needs to be stable. That's why we design the whole thing first and test it out. Then you need to make sure that with the booster stage on, it is still going to be stable. In that case, it is. As a matter of fact, we could make these fins slightly smaller. Why don't we make them? I don't know. Let's scale them. Let's see. We're going to edit them. We're going to scale them. Scale from 1.25 to 1.15. Let's see what that does. Scale. Now, I'm not necessarily saying I want smaller fins. What just happened? Did it scale? It didn't scale. Scale. Did I just scale the whole rocket? I didn't mean to do that. No, I didn't. I didn't do anything. All right, so I'm going to right-click on these fins. I'm going to scale the fins. And only going to scale these fins. Scale them from 1.25 to 1.15. And then I'm going to click Scale. And why isn't it scaling? Well, it's academic. I don't need to do this. Anyway, look what we've got here. We have a booster. We've gone from, what was it, like 1,700, 1,800 feet to 2,589 feet with these two motors. Let's do a flight simulation here. Run simulation. All right, so, whoop, we got a little warning here. What's going on with this warning? An error occurred during forward end of airframe is open, radius is 0. Body tube. What's going on? Do I have mismatched body tubes here? 0.71 or so. 0.71 diameter. 0.71. I don't know what that means. I don't think that's a problem. So we have an optimal delay of 0.696. So it's a 7-second delay for that upper stage, which is great. Still kind of a fast ground hit velocity, 31.7 miles per hour. But we got a cool looking rocket. I mean, look at that. That's pretty rad. Now, what would we get if we took away the launch lug? Launch lug does add some drag. Delete it. The launch lug, we got to gain another, what was that, 100 feet? 2633, let's see, 2633. I forgot what we just deleted it, and I've already forgotten what we undo delete launch lug. $26.33, yeah, $25.91. So that's, 40-ish feet with the launch lug. Of course, if you're going to fly like a contest rocket, you're going to use something called a piston, and that can impart some extra oomph to the rocket, and you may actually well outperform. So far we've got a high-flying, even though it's a 4-finned rocket, we've got a very high-flying 2-stage model rocket that will carry the payload of the altimeter that we have to a very high altitude. You're not going to see this rocket, basically. You hope that you see it when it comes back down, or you'll lose your altimeter. That's one of the risks of this hobby. But there we've just designed a whole rocket there. And what we can then do, once we have this, is we can actually, let's see if I can show you how to do it here. Print design info. Now, those of you who were with me last week, you know that this is a new version of OpenRocket. I have not used it much. Let's see. We're going to, first of all, we're going to save this rocket. I haven't saved anything. What would have happened? We're going to call this one Flechette. Nope. What are you doing there? Don't do that. I have set some of my hotkeys, unfortunately, to, I guess I've set some of my hotkeys to actual keys that I need to type with. I'm calling this one Flechette, which is a French word which means dart, because it is, I speak a little French, and it is thin and skinny, and it flies fast, and so I'm calling this one Flechette. So that's Flechette, and look at that, pretty cool. Now I could go back and I could make modifications if I wanted to. I could make it a 3-finned rocket if I wanted to do that. If I wanted to, please the people who say you have to have a 3-fin rocket if you want ultimate altitude, which is true-ish, but that's okay. But that's pretty cool. And then let's see. So can we print design info? Yes, we can. So what we can do is we can print everything, and it will save all of this information, or we can just print the parts that we want. So I'm going to just save this as a PDF. And we're going to just save it to the desktop. And then I'm going to bring it up and see what it looks like. And that's what would print. So let's go to the desktop. Well, all right, so let's just open it up and see what we got here. So normally with a kit, you get all your parts. You usually with Estes kits, you get pre-cut laser cut fins. With old kits, you wouldn't necessarily do that. You would get a template, you would trace it on some balsa, and you would cut it out. And so some companies that operate now, such as Fliss kits and others, you get the old-fashioned kind. You get a piece of template on a piece of cardstock, you cut that out, you lay it on some balsa, and you cut it out. So now we have a parts detail. We've got the rocket's design with its name. This is great if you're going in high power and you need to, show somebody your design for whatever reason. This will print out a lot of stuff that you can then use. It'll show you the information that we have simulated here. It'll show you your parts detail. These are your marking guides for your body tubes for marking where your fins go and your launch lug. And if you've built a model rocket before, then you know how to use that. The only thing you might need to know how to do is cut out your own fins. And you've got forward fin and aft fin here. You just trace these onto some cardstock and cut them out. And then the only other thing you might need to do is to cut body tubes to length. And it's really not that difficult. That's a skill that you can pick up. One of the things that you can simply do is you can wrap some paper around where you want to cut it as a sort of a marker, and then take your hobby knife and very carefully turn and cut. There are also tools you can get or make to help you cut these tubes cleanly. It's really not that hard. So then you measure the tube to the length you want, you cut them, you assemble all of your parts, your nose cone, your fin stock, which you just buy balsa sheeting, little centering rings like this one for a nose block or for an engine block, which you can get on all kinds of websites, John Rocket, AC Supply, ASP, that's a great one. And, then you just assemble the rocket as you would assemble a rocket kit. It's basically the same as building a rocket kit. It's just you're making your own. You're making your own rocket kit, and you've got this cool rocket. It's your own design. It'll fly very high. It'll be very impressive, and you should make several of them because you'll probably lose at least one or two of them. All right. Well, that was a lot of fun. I hope you enjoyed that. Did I even get through all of my stuff here? I think so. Yeah, I showed all of the pages I wanted to. The only thing I didn't do was take a break, which is fine. So I just set that up in case I needed to. All right, well, that was a lot of fun. Did stumble over a few things. I hope that wasn't too awkward. I hope that the stream saves as a video, because I know we had some buffering issues earlier. If need be, I might try this again. We didn't have a lot of people viewing all at the same time, so I don't really have a problem with doing this again. It was fun, and if this turned out to be a rehearsal, well, so be it. I'm planning on doing a lot more live streaming, hopefully once a week. I am going to be doing one tomorrow night. It'll be shorter, and we're going to be recording some parts and bits for the Model Rocket Show, my podcast. We tried to do this once before, and the everything was so glitchy that basically the stream wasn't working at all. And so I think I've ironed out most of the kinks here. Sorry about the weird buffering earlier. I think we got that figured out. But if you want to join me tomorrow, 8:30 Eastern, we're going to be recording the Model Rocket Show. And, of course, if you're a fan of the Model Rocket Show, you've been wondering where it is. It's been on hiatus for 2 years. We've been busy. I've been busy. But we've got a show in the can, and we've got more coming on the way. So hope you had a good time. I had a good time. And, yeah, have a good night. Thanks a lot. Catch you next time.